Hi everyone, welcome to a new unit. This is Unit 2 called Physical Change. Now, this particular unit is very different from the one that we just did. There's less math, for one thing, and most of the concepts are more abstract. So you'll have to use your imaginations for a lot of things, but I'll do my best to try and draw as much as I can in terms of what we're looking at. So in terms of what this unit is all about, it's basically about matter. Now, you've probably been asked before in grade 8 or maybe even younger what matter actually is. And if you said matter is made up of, or anything that's made up of atoms, then you're right. Okay? Essentially, everything that we have that exists is made up of atoms. So matter is just a collection of atoms. So if atoms make up everything that we know, then how does it change? Okay, you've already examined how atoms change in our last unit. It can change through chemical reactions. So chemical reactions, where these particular types of changes create new substances. So new substances are created using the same atoms that we started off in the first place. So all the atoms that exist in the reactant side will basically be the same type of atoms that you have on the product side. They've just been chemically rearranged. Now, the other change happens physically. So we have physical reactions. Or sometimes they're just known as physical changes, which is the whole basis of this particular unit. Here, there are no new substances that are formed. The only thing that forms, that looks new, is just the rearrangement of these atoms. So it's a rearrangement of atoms to produce different states of matter. Okay. So you still have the same substance, it's just been altered a little bit, okay, in terms of its appearance. And sometimes when you do that, you also alter their physical properties. Okay? Not chemical properties, but physical properties. So to get an idea of what's going on here, we should actually talk about the different states of matter that exist. And most of you guys already know the three big changes, or the three big phases of matter. Okay, so states and phases are often synonymous. They mean the same thing. So we'll say phases slash states of matter. You should already be aware that most of the time we start with solids. Okay, they go through changes to become liquids, and then we get gases. Okay, these are our three pillars. They basically make up the bulk of what we see on planet Earth. Okay, so we know that we have a lot of things that are solids, we have a lot of things that are liquids, and we have a lot of things that are gases. Okay, so some of the things that we can do is we can take a look at these in a little bit more detail. So let's do this. I'll bring this image up a bit. It looks a little bit better than what I can draw. Okay. So we all know that if you have solid water, okay, you get something like ice. So example, ice. Okay. For liquids, you have water, and gas, we have steam, for example. All three states is made from the same substance. Okay. It all equals water as in H2O, or ice as in H2O, or steam as in H2O. They're all the same substance, just different phases. So there are different phases with different physical properties. Okay. Now we'll look at physical properties in a separate video, okay, in a separate lesson, because we can spend a lot of time on just looking at physical properties of solids, liquids, and gases. For now, we'll look at a little bit of their differences. So in terms of their arrangement of atoms, so this is their arrangement of atoms. For solids, you can see that each atom is closely packed together with its neighboring atom. Okay. So we can basically comment on their atoms being densely packed. They have a definite shape to them. Okay. But at the same time, even though you don't see solids moving, okay, when you look at the individual atoms, okay, they're not fixed or still. Okay, they may be fixed in their same location and position, but they're still vibrating. They're still moving. Okay, so it's not like they're just sitting at rest. So atoms are fixed, but still vibrating in place. Okay. When we look at water molecules, okay, water molecules do something slightly different. They're not as densely packed, okay, but they don't necessarily have a shape either. Okay, so if you look at liquid water, if you pour over a table, it doesn't really have a definite shape that you can describe. So, no definite shape. And since it has no definite shape, it often takes the shape of its container. Now, in terms of its movement, these atoms, they basically slide past each other. So atoms slide past each other. That's why you kind of see this flowing movement to most liquids. So if we were to compare and contrast between the solids and liquids in terms of how they're moving, I would probably draw a solid out looking more like this. They have strong bonds that hold them in place, but because they still vibrate, there's still movement. It's just that that movement is fixed in a specific location. Whereas if you look at liquids, some of those bonds are broken, so that's why they can be a little bit further apart. Okay. So maybe I'll just draw like 2 sets here. But you have a series of atoms that can slide in one direction and the other can slide in the other direction. Okay, so they can slide past each other. That's how you get that flowing kind of movement. Okay. And then of course you have your gases. With your gases, again, there's no definite shape. They're not very dense at all, okay? And because they don't have a definite shape, they also take the shape of their container, okay? But more importantly, they tend to, the atoms tend to move around very, very randomly. They spread out. Okay, so atoms spread out to fill a container. And we describe the movement of these atoms to be random. So atoms move randomly away and or towards each other. So the way that we'll represent that is just to have a few atoms that are very spaced far apart, and they could be moving in different directions. It all depends on how much energy is present, or even the size of the container. But these are your basic 3 phases. Okay. However, there is another phase other than gases. So if we start at solids and we move up to liquids and then we get to gases, there is a 4th phase, okay, of matter. So if we go back up to the top here, okay, there should be something else that's after gases. The problem is it's not a state of matter that is easily found on Earth. Okay, so for example, if you do know what that 4th state is, okay, that's great. But if you don't, maybe these images might give you a hint. So over on the far left, we have a sun. Okay, over here we have lightning, and here you have a plasma ball. That last one should give it away, because it actually has the name of the of this particular state. Okay, that 4th state is called plasma. So there is a 4th state. And it's called plasma. Oops. Spelled that incorrectly. There we go. So when you look at the sun, okay, we all know that the sun is a star. Okay, hopefully you guys know that too. It's the closest star that we have to planet Earth. But what you probably don't always think about is, well, most people sometimes call it a fireball, but it's not really made of fire. Okay, and if you didn't know that, then this is going to be a shocker to you. The sun is actually nuclear powered. It's not fire at all. The sun is a ball of plasma. So sun/star made of plasma. Plasma is the most abundant state, okay, in the entire universe. Okay, 99% of the universe is actually in the form of plasma. So 99% of matter in the universe is made of plasma, or it's in that state. Okay. And the reason is, well, when you look at the universe, it's mostly just empty space, and then within that empty space, you have a whole bunch of stars. Okay, and around some of those stars, you have, yeah, a few planets that are solid. Okay, some planets that are gases, right? And then on those planets, you might have some liquid, but it's not a lot compared to all the stars in the universe. Okay, but on Earth, the only form of natural plasma is created when we see a bolt of lightning. So natural plasma is seen during thunderstorms. With lightning. That is our natural source of plasma. We can also make an artificial source of plasma, and that's in a plasma ball. So we can consider it quote unquote artificial created plasma. Okay. So you might be thinking, okay, well, plasma is probably, electricity. Electricity is flowing electrons, okay, which is close. It doesn't involve electrons. But plasma itself, okay, as a state, plasma is simply ionized gases. Meaning, if we give gases enough energy, they become ionized, meaning that electrons will be ripped apart from their atoms. So, electrons pulled away from atoms to form ions. Okay. And that's really what it is. So if we go back to our states of matter, okay, you're gonna need a little bit of room here, okay. We'll start with solids in a box. We're going to have 4 of these boxes for each of the states. You're going to have liquids. You're going to have gases. And you're going to have plasma. Okay. The plural of plasma is still plasma. So if we started with each one of these states, right, we should be able to go back and forth between the 4 different states. So let's start with solids. to turn a solid into a liquid, what's the name of the process? Okay. What do you have to do to a solid to get a liquid? Well, you're going to have to add heat. So if you think of ice, right? You're going to have to add heat to ice so that it will turn into a liquid. But what's that process called? Well, you guys know it as melting. Okay. So solids with heat melt into a liquid. If you continue to add more heat, you'll eventually get a gas. But the process here is known as boiling. Okay. It's not evaporation. Evaporation is a different process. Okay. You can still turn a liquid into a gas, but it's done slightly different. Okay, so we'll look at evaporation next time. Now, from gases to plasma, this one should be unfamiliar to you, okay, in terms of a name for a process, because again, we don't see a lot of plasma on planet Earth. But the term or the process is called ionization. Okay. And if we can go one way, we can definitely come back the other way. So going from plasma to gases, this is called recombination. Okay. Doesn't happen that often, okay, at least not on planet Earth, and not so much in the universe either. But if we can get those electrons back, okay, we actually recombine it with their ions to get your gases back. When you go from a gas to a liquid, that's a little bit more common for you guys. Does anyone know the term? It's called condensation. So when something condenses, it's going from a gas state to a liquid state. And then finally, from liquids to solid, this is called freezing. So freezing is just the reverse process of melting. Condensation is the reverse of boiling. Recombination is the reverse of ionization. Okay. These are all very familiar terms. Okay. Maybe not so much for ionization and recombination, but definitely boiling, melting, condensation, and freezing. Okay. Now, before I end everything, there are actually two other processes that you may or may not have heard of. I'm betting you haven't. Okay. It's possible for us to go from solids directly to a gas phase and skip that liquid phase. This process is called sublimation. Okay. And we see this happening with one really specific example. Okay. Have you guys ever heard of dry ice? Dry ice is basically a block of dry or solid carbon dioxide. Okay, and when it sits at room temperature, it will sublime into carbon dioxide gas without entering a liquid phase. So it's solid CO2 changing to gaseous CO2. Okay. In a future lesson, we'll actually talk a little bit more about this dry ice, and we'll also look at a little demo that I will prepare for you in terms of another substance going through sublimation. But if there is a process that goes from solids to gases in one step, then of course there is a process that goes from gases to solids in a single step. This is called deposition. Okay. deposition is the opposite of sublimation. And the example that I'm going to give you here is likely going to be one that I will show you in class, and it's iodine gas. Okay. Iodine gas will definitely go from iodine vapors to iodine crystals. And it's a lovely process because the iodine that we have is actually a purple gas, and it creates purple crystals. Okay, that often looks very lustrous and shiny as well. So these processes that I've listed here, we will go through them in a little bit more detail. We'll look at how solids transition to liquids and transition to gases, and we'll look at all the energy that's behind it. We'll look at how, like, what's going on with the atoms as they're doing this. We'll look at all the different factors that may affect these physical changes. So all in all, this is a pretty good point to end this end this video. It gives us a nice introduction to what you're going to expect for the next couple of weeks. So until next time, okay, stay safe, guys. See you.